Okay? Should I revise once again? We have started from here. We have the given determinant matrix. It was a revisional question. It was given as homework yesterday. We have the adjoint of A, determinant 22. Further, A into adjoint of A calculated, and that happens to be A into adjoint of A is equal to, we have already seen it is 22I3, that is determinant into I. Now we are going to make that as a theorem. If A is any square matrix, and be careful about that. Any square matrix of order n, then A into adjoint of A is equal to adjoint of A into A, that is determinant A into I, where I is an identity matrix of order n. Let us see how we make a proof. Proof is not a serious one here, but it is very simple if it is given as a question. Look at, you have the matrix A and its adjoint. Adjoint is the transpose of cofactor matrix A11, A12, A13. The cofactor of that will come in the first column because we are taking the transpose. A21, A22, A23. The transpose of that comes here. A31, A32, A33. That is the third column. Now when you take A into adjoint of A, matrix multiplication is a row column operation. First row with the first column. First row with the first column. First row with the first column. This is A11 into capital A11 plus A11, A12 into capital A12 plus A13 into capital A13. We know that is the determinant of A. We have stated that theorem yesterday, proved also. The sum of the products of elements with its own cofactors will give the determinant, whereas A11 into A21 plus A12 into A22 plus A13 into A23. These are the cofactors of second row. So elements of first row, cofactors of second row, it is 0. Similarly, elements from first row, cofactors of third row, that is also 0. When it comes to second row, elements of second row with the cofactor of first row, that is again 0. Elements of second row with the cofactor of second row, that is the determinant of A. Further, second row and cofactors of third row, that is 0. When it comes to third row, elements of third row, cofactor of third row is determinant of A, the remaining 0. And hence that is equal to determinant A taken out. It is in the matrix 1 0 0 0 1 0 0 0 1. That is determinant A into identity matrix. So what we have seen is, similarly we can say A into adjoint of A is determinant A into I. Similarly, adjoint of A into A is also determinant A into I. So we have a result here. A into adjoint of A equal to adjoint of A into A. That is equal to determinant A into I. Well, let me just make some more definitions here. A square matrix A is said to be singular if determinant A is 0. Singular matrix. If determinant A is non-zero, it is called a non-singular matrix. You have to remember it. Questions may come, short questions. When is a matrix singular? When is a matrix non-singular? Let's take example. This is a singular matrix. Why is it singular? Because its determinant is 2 8 16 minus 4 into minus 4, that is 0. It's a singular matrix. This is non-singular. Why? Because the determinant is 26, non-zero, hence it is non-singular. Normal question comes here. Find the value of x if the matrix A is singular. Can you guess and tell me the answer first? As A is a singular matrix, determinant A is 0, or 2x x 8, that is 0. That is, tell me what is x? Hello?
Yes, sir.
Tell me what is x?
Sir, x is equal to plus or minus 4.
X equal to? Yes, you are right.
Sir, 4 and
Plus
minus
or
4.
minus 4. Plus or minus 4. Both are valid. Okay. Now you can have if the question find the value of x if the matrix A is non-singular. Non-singular means determinant must be non-zero. 3 minus 2 x 4 is non-zero. That is 12 minus 2x not equal to 0, or 12 plus 2x not equal to 0. Then what is x? X not equal to minus 6, or x belongs to R minus 6. Non-singular and singular matrices. Getting along? Now we have theorem. A and B are square matrices of same order. Determinant of AB is determinant A into determinant B. We take this granted without a proof. Determinant of the product of two matrices is the product of the determinants. Simple one, applicable. We can apply many places. Next one again. A and B are non-singular square matrices of same order. Then AB is also non-singular. Quite simple. Proof can be made from here. Very simple. I'll give this as a question later. If A and B are non-singular, then AB is also non-singular. Okay. Further we have, if A is a square matrix A is invertible if and only if A is a non-singular matrix. That means every non-singular matrix will be invertible. If it is singular, it is not invertible. Let us see. This is to be established a proof. Let me go for a proof. Proof is very simple. A square matrix A is invertible if and only if it is a non-singular matrix. Let me start with let A be non-singular. Once we have a result here, we have proved earlier. Determinant A is non-zero, and we have already seen A into adjoint of A equal to adjoint of A into A, that is determinant A into I. That is the first theorem which we proved. Well, what happens if I divide? By dividing throughout with the determinant of A. Look at, if I divide with the determinant of A, this will be I. This will be 1 by determinant A into this. Again, I can divide with 1 by determinant A will be here, because determinant A is non-zero. Dividing throughout with determinant of A, as determinant A is non-zero, I get 1 by determinant A into, is a number, into A into adjoint of A equal to I, that is equal to 1 by determinant A into adjoint of A into A. Is it clear? I divided both sides, all the three sides, with determinant of A, because determinant A is non. Now this I am going to rewrite in a different way. This is a constant. 1 by determinant A is a constant. I am joining with adjoint of A. So A into matrix A into 1 by determinant A into adjoint of A. This constant I can take with this equal to 1 by determinant A into adjoint of A. I am taking that number with this matrix into A, and that is I. Is it not of the form A into A inverse equal to A inverse A equal to I? In that case, what will be the inverse of A? You can read from that. This is the form A inverse equal to A inverse A is identity matrix. Can you tell me what will be the inverse of A in this case? If you have AB equal to BA equal to Y, the inverse of A is B. If you have AC equal to CA equal to Y, inverse of A is C. Can you tell me the inverse of A from here? Preksha. Hello, can you hear me? If you have AB equal to BA equal to identity matrix, the inverse of A will be B. Here you have A into 1 by determinant A into adjoint of A equal to 1 by determinant A into adjoint of A into A equal to I. We are getting it from A into adjoint of A equal to adjoint of A into A equal to determinant A into I. I divided all the sides with the determinant of A. I get an equation like this. From here, can you tell me what is the inverse of A?
1 upon determinant of A into adjacent of A.
Very good. A inverse will be, so one thing is true here, which shows that A is invertible, and the inverse of A is A inverse equal to 1 by determinant A into adjoint, ADJOINT, not adjacent, adjoint of A. A inverse is 1 by determinant A into adjoint of A. What is the requirement? Determinant A must be non-zero. Very important result you cannot ignore. If A is non-singular matrix, that is determinant A is non-zero, then A is invertible. That is the first point. That is A inverse exists. And what is A inverse? 1 by determinant A into adjoint of A. This is a formula, you have to remember it. Proof is a secondary thing, but you have to remember. If determinant A is non-zero, A is invertible, and the inverse of A is 1 by determinant A into adjoint of A. Now, if you want to find the inverse, you know how to find the determinant first. Then only you can decide whether inverse exists or not. Then we go for the adjoint. Once you get the adjoint, we can write the inverse. What happens if determinant A is 0? Then of course, A inverse does not exist. In that case, the matrix is singular, A inverse does not exist. Okay, before going for this problem, let me just take some example. Find the inverse of the following matrix if it exists. How will you first find? First go for determinant of A. Determinant of A is 1, which is not equal to 0. Minus 15 plus 16, that is 1. So what happens? The inverse exists, and what is inverse? 1 by determinant A into adjoint of A. Can you tell me what is adjoint of A here? You remember how to find adjoint of 2 by 2 matrix? Diagonal elements interchange, other elements change the sign. Diagonal elements interchange, we already discussed. Diagonal elements interchange, other elements change the sign, and we got the adjoint. Once you get the adjoint, A inverse is 1 by determinant A into adjoint, that is minus 5, 2, minus. I told earlier, I will tell you how we can get the inverse of a 2 by 2 matrix directly. First find the determinant, 1 by determinant into adjoint of a 2 by 2 matrix. Can you recollect? I told earlier. Now I am telling how to find the inverse of a 2 by 2 matrix. What is here? How to find whether it is invertible or not. What is the determinant? It is 2, which is not 0. Determinant will play a role later. And what is the, so A inverse exists, and what is A inverse? 1 by determinant A in adjoint of A, and that adjoint of A is, we got it by interchanging the diagonal elements, other elements change the sign. So A inverse is 1 by 2 into 2 minus 3 minus 4. We can keep that 1 by 2 outside, no problem. Or if you take half inside, it will be 1 minus 3 by 2 minus 2 and 7 by 2. You can keep. You can keep this way or taking half inside. Okay. Well, I am giving this as a question to you. Let us see if A and B are non-singular square matrices of the same order. Prove that AB is also non-singular. How do you prove? Proof is very simple. A and B are non-singular matrices. So determinant A is not equal to 0. Determinant B is also non-zero. So what happens? Determinant of AB. Determinant of AB is determinant A into determinant B. These are two real numbers. Non-zero real numbers. Their product is non-zero. Determinant of AB is non-zero, right? That means AB is also a non-singular matrix. Once determinant AB is non-zero, AB is also non-singular. So if A and B are non-singular matrices, square matrices, of course it must be the same order. Then only AB is defined. If A and B are non-singular square matrices of same order, then AB is also non-singular. The main point is how to find the inverse of a square, inverse of an invertible matrix. First, identify whether inverse exists or not. Well, I am giving you 1 or 2 questions for you to find the inverse. Please note down. Remaining questions you have to note down from your booklet given to you. Inverse of matrix. Now it should be very fluent in that, how to get it. That plays the major role in further. 2 by 2, you can easily tell the answer without much step, but here you need to do it. That is your job now. You have to do it today itself. You have to find the determinant. If the determinant is non-zero, then only the inverse exists. If the determinant happens to be 0, we can state that the matrix is singular and the A inverse does not exist. And again, for this, both the matrices, this is simple. You have to do it. This again, you have to do without fail. Tomorrow when we meet, I want the inverse to be very fluent, and I want the inverse from your side. Okay? Enjoying well? All the best. Have a nice day.